Yeah, so I'm going to be talking about this really is the background for a big chunk, well, a medium-sized chunk of the AxoNobel project, and it's really thinking about what effect polymer interfaces have on mobility and transport. So, as I say, it's part of the AxoNobel project. This is about Work Package 2, Polymers and Interfaces. And so I would like to acknowledge the team that we've got. As I say, I'm going to be focusing on one specific issue. The specific issue I'm going to be talking about is mostly the area that Stephanie Berg has been focusing on. But I'd like to acknowledge all of our collaborators at Sheffield, at Manchester, and at AXO, and particularly to our AXO colleagues, not just for giving us the being the initiators of the project, but also I think for some really useful and important intellectual input, and I think I want to make a general comment about that later on. So thanks to everybody for that. The problem really is this. Okay, supposing we've got a substrate, we've got a film. In this case, I'm imagining a protective coating film made from some kind of epoxy. There's a whole bunch of stuff going on in there, and there's a whole bunch of stuff happening in the kind of perpendicular to the plane of the film. These are not homogeneous systems. And so we can think about how water diffuses. We can think about the changes in the physical properties, and all these things are coupled. So the glass transition temperature coupled to these properties. We've got some ways to measure them. And there's a whole bunch of variables to change. But the thing I want to just focus on here is the polymer substrate interface. I want to think about what happens at an interface between the coating layer and the polymer itself. And I really want to argue that that interface is quite important and quite different. Well, certainly not necessarily the same as the interface in the bulk material. And of course, what I'm talking about, I'm going to be talking about polymer solid interfaces. And of course, having seen Jan Wen's lovely talk, that reminds us that actually a heavily filled sample actually has a huge amount of interface in it. So in terms of the amount of polymer that we can consider as being bulk, it's difficult to very little of the polymer in a sample of the kind that we saw in Jan Wen's talk actually looks like bulk material at all. It's almost all interface. Well, the question there is how near do you have to be near to the interface? What's the range? What do we mean by that? So maybe something will happen eventually if I keep pressing. Yeah, okay. So when we need transport, so corrosion does involve transport, transport of water, involves transport of ions to that interface. And ultimately, we'd like to be able to model this. We'd like to be able to model this as a whole bunch of coupled diffusion processes. So we have collaborators in the overall proposal who know well how to do that. But the most important part of the journey is this final step, that last few nanometers to the interface. And so really asking this question, what's going on in those few nanometers, I think is quite important. So what could happen is a bunch of different things. It's not the same as the bulk, for reasons that I'm going to go into. And there are a number of different ways in which it's not the same as the bulk. So really the question I'm asking here, people talk about the interface. The interface is used as rather a loose term referring to that polymer that's influenced by the interface. But so what I'm really asking is, what do we actually mean by the interface? What's going on in there? And I think that there are a number of different things. It may well be a region that has chemical heterogeneity. So we may have absorption of and segregation from the different components of the resin, and equally we might have diffusion from the substrate out into the material itself. So that really was a subject of Suzanne's very nice talk yesterday. This morning. Time flies. And so I'm not going to talk about that further right now. As I say, I think that's one really important aspect of it. And, I think there's some really important, there's some fundamental physical reasons why absorption is particularly important in macromolecular systems. And so it's not a surprise that those are important factors. There may be inhomogeneity in cross-link density, so that again may be connected to the question of absorption. If the cross-linking agent is preferentially, there's an inhomogeneity of that may lead to inhomogeneity in the cross-link density. But what I want to talk about now is actually something that's, in a sense, even more fundamental, well, not really fundamental, even simpler in the sense that even in the absence of chemical heterogeneity, inhomogeneity and cross-link density, there is the question that the substrate itself may induce changes in chain mobility that will affect diffusion properties. And so that's really what I'm going to talk about today, is a little bit of a history of that subject and some thoughts about where we're going with it. Yes, that's what I'm going to talk about, because it's in red. So, why are we interested in this? Transport in polymers. I want to just comment on length scales and time scales in polymers. So, the diffusion of a molecule in a polymeric matrix is something that one shouldn't think of this diffusion process as being like the diffusion of or the transport of a fluid in a porous structure where, you've got a hard porous structure and you've just got stuff going through a path. You've got, well, in fact, in a sense, there's a kind of, you can think of a continuum here. You can think of two extremes. One extreme would think, I've got a porous material, like a sponge made out of glass. The water goes through the pores. At the other extreme, you can think of something like rubber. If you ask the question, how does cyclohexane diffuse through rubber? Basically, as far as a cyclohexane molecule is concerned in rubber, it's in a fluid, because the local behavior of a rubber is essentially fluid-like, and in that case, you can you should think of it as being essentially fluid-like diffusion. But so in general, there's got to be between those extremes, there's kind of a coupling between the penetrant diffusion and the chain motion. And so for my blue blob to go from the left to the right, the chains have got to move to get out of the way. And a key point is that there are lots of different timescales in chain motion. So chains can wiggle on a very short time scale. They can wiggle over a short distance, and they can wiggle, and that'll happen quite fast. They can wiggle over a very long time scale. They can have one of these long breathing style modes. Those are very long time scale modes. But there's a fantastic kind of principle of polymer physics called time-temperature superposition, which essentially says that all of those things have the same. There's this superposition between time and temperature. That every motion essentially has the same temperature dependence. So formally, I can kind of factorize. If I write down an expression for a relaxation time, I can factorize that as a bit that depends on temperature and a bit that depends on length scale. And so that's a kind of marvelous general principle. That's something called time-temperature superposition. What difference do cross-links make? Cross-links actually make some difference. They constrain long length scale motion, but they still allow small scale motions. So this idea of time-temperature superposition tells us why the glass transition matters. Glass transition temperature, as polymer physics, elementary polymer physics tells us, is an indication of mobility in the polymer, because what happens is that the glass transition takes place when the time scale of the time scale for those kind of configurational changes drops below the experimental time scale. And because all the motions in a sample, in a bulk sample, have the same temperature dependence, in the sense the glass transition, it kind of it takes into account all the types of motion that the polymer can have, small wobbles and big wobbles. And so, as you know, classically one finds in textbooks, you see the glass transition as a dynamic transition, not a proper thermodynamic transition, but it shows up in second derivatives of free energy as so it's a discontinuity in slope of things like volume and enthalpy. And it tells us what's going. It gives us indication of mobility in the polymer. And as I say, it probes average motions on the timescale set by the experiment, and the timescale set either by the frequency or in a cooling rate in the DFC experiment. And roughly speaking, just the relationship between mobility and the measured temperature shift is essentially exponential. In really kind of, if you want a rule of thumb about it, if you get a 3 degree shift in glass transition temperature corresponds to about a factor of 10 in the time of any relaxation time you've got in the material post glass transition. Anyway, so what's this got to do with interfaces? Well, a long time ago, and Simon reminds me that this was actually done in another collaboration with industry, in that case with the late lamented ICI and some others. The question was asked to me by one of Simon's colleagues in ICI. Sometimes I kind of roll up my PET films and they stick together, even though it's a semi-crystalline polymer that's below its glass condition. How can you have any adhesion? And Peter Mills, as it was, said, you know, Richard, are you really sure that the surface is actually the surface is glassy when the bulk is? And so we devised an experiment to probe this, and in fact we found that this decrease in glass transition temperature, when you went to film thicknesses below, certainly starts below 1,000 angstroms. By 100 angstroms, the drops are quite substantial. So that was done by Joe Keddy, who's now at Surrey, who was then a postdoc with me, and Rachel Corey. I just mentioned Rachel Corey. Rachel Corey, actually, the first experiments were done as a undergraduate project, and Rachel Corey was the undergraduate student who did it. And actually, it was a really kind of difficult time. Rachel Corey was in her final year as a student, and then she had leukemia, and she had a kind of a relapse of that in about sort of January, and she said, oh, look, I really want to carry on doing these experiments. And she really did about 4 of them, did about 4 data points, demonstrated the effect worked, and then before final she actually died. So it was a kind of I do remember Rachel when I see this data set. But things are not straightforward. Lots and lots of people have done this experiment, and maybe if I'd realised it would cause all this trouble, I wouldn't have started in the first place. But there has been a lot of controversy. This recent paper from Friedrich Kramer, it's a great catalogue of all known measurements of TG in films of polystyrene. And as you can see, there's lots of techniques used, lots of different experimental setups. I think it's fair to say they all show a reduction in TG, but there's kind of there's not as much consensus as you'd like about what the quantitative nature of this effect. I think this is people who do science studies, STS, sometimes talk about an experimenter's regress. There are a bunch of problems where there are so many confounding variables about, you know, what's the precise nature of the surface, what's the precise preparation route for the films, have they been aged, have they been, all the different things that you can consider, that it's actually quite difficult to come up with a consensus. That's the surface. We're interested in the substrate, and roughly at the same time, Joe and I did some measurements, in fact, of on some different surfaces in PMMA. So PMMA as a polymer that has a bit more of a strong interaction with an oxide surface, that shows actually an increase rather than a decrease. And at the same time, some experiments from in small molecules in pores actually also showed the same sign. Again, orders of magnitude of 10 to 15 degrees. And again, I say 10 to 15 degrees may not sound very much as a transition, but remember that kind of that exponential relationship. And that's probably a factor of 100 or 1,000 in relaxation time. So it's a big deal. So it's really tempting to say what's going on in something like this. You've got a surface. You've got a more mobile layer in the surface, you've got a bulk-like layer in the middle, you've got a less mobile layer at the substrate. And I think there is some direct evidence for this from spatially localized TG measurements and fluorescence from John Torkelson, which Stephanie doesn't believe, I shall just mention. Again, nothing is straightforward in this discipline. And another nice piece of data, which I think is actually very relevant to us, so Sanat Kunar's group demonstrated that in filled systems, you can see a kind of a change in TG that is, you can think of a filled system as being a system that's confined, that's got a lot of interface near it. And you can say that there's a kind of rough correspondence between what you measure in a thin film and what you measure in a filled system. And in that case, so that's silicon oxide, polystyrene on silicon oxide, where as the interparticle spacing becomes smaller, the TG is reduced. But again, I just want to kind of point out the length scales. It's kind of important to get this length scale in your head. You're talking about tens of nanometers. So on this basis, if you think, what is the interphase? The interphase, by this basis, even in a chemically pure system with no chemical heterogeneity, that's my answer to the question, really. It's of order 10 nanometers. I also should mention, from the point of view of theory, it's a matter of amusement in Sheffield that I don't believe in free volume theory, but this is a very nice refinement of free volume theory from Jane Lipson, which you can kind of persuade yourself actually does show how you can get a relationship between substrate interaction and TG. So for no interaction, the mobility is higher. For lots of interaction, the mobility is lower. And you can imagine turning a knob, and as you turn the knob on, you reduce the mobility near that substrate. So that's what theorists can do. They don't have to worry about all this kind of experimental complication. We can show that these effects matter in epoxy resins. There's actually some data from Andy showing slowing of dynamics due to the added interface with silica particles. Let me just go about technically how do we do this. The way that Joe Keddy and I originally started measuring thin film glass transitions was with ellipsometry, and this is based on this idea. The glass transition, as I say, it's a discontinuity. It's not a thermodynamic transition, but it shows up in thermodynamic quantities, and it shows up in second derivative quantities of free energy. So if you use a DSC, what you're measuring is a discontinuity in the heat capacity, which is a second derivative quantity of a free energy, but expansivity is actually also a second derivative quantity of a free energy. So it shows up as a discontinuity in the expansivity. So if you measure the thickness as a function of temperature, you should see it as a break in the curve. So that's it's well, it's not a straightforward experimental setup, but if you've got a nice ellipsometer, you can do this experiment. And I should just point out at the moment that this is an experiment that's asking a huge amount from an optically based technique. if you want to measure a glass transition temperature in a 10 nanometer film, you're measuring fractions of an angstrom. So you're depending on being able to use an optical technique with a wavelength of 500 nanometers or whatever, and you're expecting it to be able to tell you about a quantity, a length scale of order, a tenth of an angstrom is probably about right. So it's astonishing it works at all. Sometimes it does, and we can adapt it with a sample chamber and put stuff in there to get an environment. So here's an example from Stephanie to show there is something going on in this case uncrosslinked 6099 film, and you can see both. You get quite nice high temperature behavior, so nice linear behavior, nice expansivity. There's clearly a break region, but there's lots of work to do, particularly as you get the films thinner than this, in being able to get out the transition region. Here's an example. It kind of looks good for a 300 nanometer film. It's fine. It's kind of, by the time you get really thin, it's getting quite hard to convince yourself there is a real transition in there. But there is clearly something going on. The expansivity is not constant. So there are some serious issues here. So in very thin films, so ellipsometry essentially is a very sensitive way of measuring path difference for S and P polarized light going through a sample. So it depends on the optical path length, it depends on the thickness that you're going through, and it also depends on the refractive index. And you can convince yourself in very thin films, you can kind of, it's a kind of moment thing. At some point, it's really only sensitive to some product or some moment, first moment of the refractive index over the path, and that makes it slightly problematic in extracting it when we get to these very thin films. So that's one issue. We also, I need to come back to this question of disentangling the effect of the surface and the interface in the thin film. And there's my picture. But of course, I've drawn my picture as a continuum. And we know these polymers aren't actually a continuum. If we've got a continuous... sorry, I should say there's two problems here. As we go from a thick film to a thin film, we're going to a situation where there is some stuff in the middle that's probably bolt-like. There might be some stuff at the front. There's a surface and there's an interface. In these very thin films, of course, we're ending up with, there is no bulk at all. Part of it's affected by the surface, part of it's affected by the substrate as a continuous mobility gradient. But the other issue is this chain connectivity issue. So this, again, this is taken from Friedrich Kramer's paper. We have to remember that these polymers are not actually, it's not just a kind of nice gradient from PowerPoint from blue to purple. There are actually molecules in there, and the molecules are actually quite big. And so there's an issue about essentially what one can say is a single segment or a single strand in a cross-linked material is going to sample different dynamic environments. And actually that's probably enough theoretically to kill time-temperature superposition, because time-temperature superposition in a sense assumes that there's a uniform environment. And actually there was a very nice paper. Well, I say there was a very nice paper. There was a paper that I thought was very nice in Nature a couple of weeks ago, which actually demonstrated, which rested on this phenomenon the other way around by looking at surface mobility in a polymer and arguing that, in a sense, at the surface, you kind of had chains that were anchored down in the glass, so they look more like a polymer brush. But Stephanie doesn't believe that paper either. But I thought it was all right. Anyway, as I say, it's difficult and controversial. So that's the reason for why this is all complicated. Okay, so where are we going with this? I think, and I think Stephanie's done a fantastic job in showing, how far can you push this technique. And as I say, I come back to this idea just to stress how on earth does it work at all to do an optical technique down at kind of sub-angstrom levels of resolution. We can get around this by using X-ray reflectivity as our thickness measurement, because X-ray reflectivity, essentially, X-rays are shorter in wavelength than light, so we have more hope. So in X-ray reflectivity, we should be able to remove that coupling between the refractive index and the thickness in the data analysis. So I showed the data from Andy, showing we can use dielectric spectroscopy to probe the timescales directly in thin films. And of course, what we do need to do is to measure swelling in ultra-thin films. That's on our agenda. Well, it's not on our agenda, we're doing it. And I think, ultimately one wants to come and say, TG is a kind of slightly indirect probe of mobility. We're interested in mobility because it affects diffusion. At some point, we want to tie this all together just by directly measuring probe diffusion through that interface region. So we can do that, and again, we have preliminary experiments using neutron reflectivity, using D2O. So yeah, my love of deuteration comes out again. That has, in principle, got nanoscale resolution, so it should be able to do that, though the interpretation is always not straightforward. So that's, as I say, that's an overview of this, one part of this problem of what is the interface. It's, if you like, the bit that's just about pure dynamics, and I think hopefully that's convinced you that there's something interesting and important going on at those interfaces when it comes to mobility, but also saying that it's not totally straightforward to work out what that is in full quantitative detail. So thank you very much.
Thank you, Richard. Do we have any question from the audience? Yes, one. Back.
Thank you for a very good talk, very interesting. I've read something about interfaces changing the ordering compared to the bulk, and I was wondering, is there an experimental method to measure that, or do you think it doesn't play a part in these systems?
Yeah, no, that's a great question and entirely relevant. Yeah, we certainly know that the ordering is something that is affected by an interface. So I mean, in a sense, we rely on that. If you've got a liquid crystal display, it relies on the fact that the interface imposes an order on the liquid crystal phase. And indeed, if you've got a liquid crystal phase, if you've got a liquid crystal or a liquid crystal forming liquid in the isotropic phase, it will, there's an order parameter that's absorbed. It's a kind of, generalized absorption. So you will see a layer that has the order imposed on it by the interface. Alcohols do that in free surfaces as well. So, I mean, we have actually studied that in a totally different system, in a semiconducting polymer, where you have, a former postdoc of mine, Tao Wang, did this and showed that in a conjugated polymer where there's a more intrinsic tendency for the thing to order, you do see that ordering. He actually also did show that there's a TG effect as well. So everything's coupled. We can do those. In principle, we can do those experiments. Well, we can measure surface-specific ordering using grazing instance X-ray diffraction. I mean, that works for a free surface. It's slightly more tricky to do it to the buried interface, but those are things that can give us a handle on that. I have to say, I would be quite surprised. Well, maybe not, I don't know. But I think I'd be surprised if it was a really important factor in epoxy systems and these cross-linking systems. But it is, yeah, it's something that happens. It is another dimension to the interface.
Thanks.
Simon?
Thanks, Richard. It's an interesting, thoughtful talk. I guess just going right the way back to the start, I mean, certainly I've experienced solid lumps of PET that are many tons because of this effect. Do you still feel that is down to this, a difference in the surface, or is there a different mechanism behind that adhesion?
No, I do think it is down to the adhesion. And I mean, that's your old company gave me a nice case award to study it with my student Anya Wareham, and I think she demonstrated quite. I was convinced that there was that, that if you measured the temperature dependence of adhesion, the adhesion process in PET quite carefully, you could see diffusion proceeding below the glass transition temperature. And my roughly, and there's other data too. There's some data from AFM measurements of adhesion that you can interpret under the assumption that, roughly, you have to remember, it's not that there's no mobility. It's not that there's no temperature dependence at all of the mobility. It's just the temperature dependence is less. And so, as a first approximation, I would assume, as you reduce the temperature at high temperatures, you'll see a kind of Arrhenius temperature dependence, an exponential temperature dependence. As you go through the glass transition, in the bulk, that Arrhenius temperature dependence is turning over into a Vogel-Fulcher temperature dependence, which is much, much stronger, really super exponential. But I think my first guess would be you can kind of extrapolate the high temperature Arrhenius behaviour down to the glass transition. But this is there's a huge amount of speculation that I'm indulging there, and Stephanie's disapproving of me for doing it. So
it's just, I guess despite the fact that I was involved in some of this work, I never connected the two. And I'd always thought, pre you doing this work, basically we were really clever, and we made really smooth materials that had so much interaction that the cohesive forces were enough to give you the adhesion. Yeah. But if there's a temperature dependence, as you suggest, then that basically is a good thing that your mechanisms are right. But
no, I think those systems had real chain interpenetration. It wasn't just dispersion forces.
Yeah. Out of small acorns or large tons of polymer films, oak trees grow or whatever. But yeah, great. No, thank you, Richard. That's very good. Thank you.
So, Richard, there is a question on the chat. Okay. So does this mean that the mobility of ionic water and oxygen move faster through the interface region?
Yeah, I think it depends on the interaction, and that's where we come to Charlie and his kind of modelling work about what is the details, what's the detailed interaction between the polymer segments and the specific chemistry of the interface. So I think it could go either way. I think if there's kind of strongish interaction, you would expect slower diffusion through that region. On the other hand, if the interaction is weak, you could imagine it being faster. So it's all down to what's the sign and strength of that interaction. So in a sense, you've got a kind of chemistry going on. My picture of it is that you have some chemistry going on where you have a local physical or even chemical bond between the polymer and the substrate, and then these mechanisms, there's a kind of interesting thing about how does the length scale of imagine you have a hydrogen bond, to make things simple, kind of PMMA with a hydrogen bond onto an OH group is kind of sort of classic picture people draw. That's a very small scale interaction, but the argument we're making here is that then gets turned into a longer scale effect that's kind of penetrating up through nanometers, and then that kind of that's then to explain that we have to invoke the ideas about cooperativity that people have in theories of glass transition. But yeah, so that's I think could be either way.